Here we're going to be looking at domain range, max, min, and modeling. Domain range, let's take a look at this diagram. I think that's the best way of doing it. Our domain are the x values that we have. So we can see here we're going from -3 to +3, and we're including those. So therefore I'm using square brackets. The range are the y values. So the lowest y value I have is -8. And the highest y value I have is +10. So my range is from -8 to 10. So keep referring to this, and that will hopefully make sense to you as far as domain and range is concerned. Of course, if this dot here wasn't coloured in, then we wouldn't be including that particular position, -5, 10. So that would mean that we'd have a circular bracket there, and would also have a circular bracket here. Local max min, you probably picked this up already from the previous bit of work, but there's my local max, there's my local min. The absolute maximum for the function given is here, and the absolute minimum is there. So around this area locally, that's the maximum value, and around this area locally is the minimum. Just with our function notation, this is the formal way of writing it. So what's the name of the function? So it's f. This is the domain for it. So these are the x values that we can have. We go from -4 to 1 including. And this maps out onto the set of all real numbers. So here, this capital R is a set of all real numbers, and the range, the values of y that we can have, will be within it. And within is the key word there. All right, it doesn't mean that as a result, we're going to have all of the values that are possible that exist in the world. That's not the case. What we're saying is that the range will be within that set. And here we have the algebraic rule. All right, so we've got this function f, where the x values are from -4 to 1. We don't know what the range is, but the range fits within the set of all real numbers, and here's the rule. We need to sketch this. So here's my function. Straight away, I know that it's x times x times x, so I'm going to get a positive cubic, so the graph is going to go up towards the right. We're going to have a maximum of 2 turning points, and then it's going to continue to go up towards the right. X-intercepts, just make f of x equaling 0 and solve for x. So you can see there I get those x-intercepts. For my y-intercept, just substitute x equaling 0 into f of x, and you can see I get 0, -8. We also need the endpoints. So remember the domain was from -4 to 1. So if I substitute -4 in, then you can see that produces 0. And if I substitute 1 into it, it also produces a 0. So here's my graph. Remember, it's a positive cubic. I've got those x-intercepts, and they're also the endpoints as it turns out. And I've got 0, -8 there as well. And then I've got my values, as you can see here. My domain is from -4 to 1, and my range is from the lowest value of y that I have, which is -8.21, up to the highest value I can have, which is 4.06, and that's corrected 2 decimal places. Let's take a look at how I can find all of that information using my CAS. So now let's make use of our CAS calculator. So define the function, menu, actions, define. And there's my f of x. It's defined. Now notice that the domain was between -4 and 1, including those values. So let's look at what y is equal to when x is equal to -4. So I just want f of -4, and it's 0. It also goes up to 1 and includes 1, so f of 1. That also produces 0. To evaluate what the y-intercept is, I just make x equaling 0, so f of 0. So you can see I get -8. And to get all x-intercepts, I'm going to solve for f of x equaling 0. In other words, y equaling 0. And they are my 3 intercepts. And as it turns out, here and here are also my endpoints. Now, if I graph that, I can go to the home screen and then go to graph, put in f of x, and there's everything. Notice that when I sketch this, I'm only going to include from here, -4 to 1. Let's take a look at where those turning points are, but first of all, let's go to our graph window and zoom. And I'm just going to change the bottom one here. I'll go to -15. All right, so I've got everything I need. Now it's a matter of menu, analyze graph, go for my maximum. So there's that one given, corrected 2 decimal places, and then analyze graph, and we'll also get our minimum. And there's that as well. So I've got all the information I need, and that's how I can come up with this sketch here. Now I've got this problem here. We've got f of x, and it's this cubic, and it describes where the river goes. What we've used here, we haven't used north, east, south, west. We've just given it Cartesian plane kind of logic here. So we've got x's and y's. And what we're interested in is what's the southernmost point of the river between x equaling 0 and x equaling 2. So what you'll see here is that we've got this position, but below it, just around here, and it's very difficult to see on this particular map, but just around here, we have the local minimum. So what I do is on my CAS, I graph it, and then, like I've shown you beforehand, you analyze the graph and find that local minimum, and you can see it ends up being -1.2 for y. So that is the lowest point on the graph between x equaling 0 and x equaling 2. So we'll just say that it's 1.2 kilometers south. In problem 3 here, we've got a water slide, and it can be modeled by this cubic. So here's the water slide, and we enter the water. Some points of interest for us is that we've got a ladder, which is 5 meters behind. We've got a vertical height that ladder makes. We've got ourselves a local minimum here, and that's been given. We've also got a local maximum, which is the peak of the water slide. And then we've got an entry point where the water slide goes into the water. We want to find all of that information out. So to begin with, what I'm going to do is define this model, and then I'm going to graph it. So menu, actions, define. So there it is, it's defined. I'm now going to graph it. And I'm just going to change the window settings. So menu, window settings. I'll go for -10, that's fine. I'll go as high as 20. And for my Y minimum, I'm going to select -2. And the Y max I'm going to select here is 12. Go OK. And there it is. I've got everything that I need. So you can see there that there's a point here where it's the minimum, got the maximum, and then when it cuts through as well. So I might just get rid of this label so that's out of the way. And where it comes through here as well. So let's look at the algebraic approach here for evaluating the y-intercept. So f of 0, you can see it cuts through at 7.2. So on our graph, that there is 7.2. So to answer our question, what's the height h1 of the top of the water slide? So here it is here. That's where we enter the water slide. It's 7.2 meters above the ground. So 7.2 metres. B, the coordinates of A, where the slide enters the water, so that's over here, which is the x-intercept. So for this one, I'm just going to use solve, so menu, algebra, solve. For the x-intercept, let's make f of x equals 0 and solve it for x. And you can see it's at the 15 metres along. So from here, we go 15 metres along, so that's a point 15, 0. The length of the ladder, well, we've got ourselves a height that's known, which is 7.2 metres. We've also got the base here of -5, but it's a base of 5 metres. To work out length, because this forms a right angle, I'm just going to use Pythagoras' theorem. So it's going to be the square root of 7.2 squared plus 5 squared. And that's shown here. And you end up with the 8.77 metres. That's what it is exact format, but that's it here. The height h2 of the mini hump to the nearest centimetre. So we're just talking about this position here. So what is that height? You can see it's 0.58 metres above the ground level here, but let's just go and verify that. So over to my graph, and I want to go menu, analyze graph, and I want this local maximum. So select there, go across, and correct to 2 decimal places. You can see it's 0.58 of a metre. And that's all the key information that I require. You'd have no chance of working with this without your CAS calculator. Problem 4 here, we're going to be using simultaneous equations to find this cubic. All right, it is actually a cubic for the following. So we've got 4 points that are known to us. So what we can say is that the general cubic is f of x equals ax cubed plus bx squared plus cx plus d. So I have 4 unknowns here, a, b, c, d. And I have 4 knowns, which are these points. So it becomes quite easy for me to use my CAS calculator. To begin with, I define f of x. So I'm saying that f of x is equal to this cubic. So f of x equals, and you need to make sure it's a times x cubed plus b times x squared plus c times x plus d. If not, the CAS calculator will not recognize a, b, and c as being coefficients. It'll see, for example, cx as being the one variable. So it's very important to put multiplication in there. We then go menu, algebra, solve, and you want to put in these equations. All right, so f of 4 is equal to 10. So when x is 4, y is equal to -10. F of 6 is 90, f of 8 is 302, and f of -2 is 2. Go comma A, and that will give us all of these solutions here. So that's what we did on the CAS, and this is how we should write it to show that you know what's going on. So what does our cubic end up being? 3/4 of x cubed plus a half x squared minus 12x minus 18. That is the cubic that will run through those 4 points.